Today, we are going to talk about using stochastic methods to identify human activities based on household sensor data. Sensors are placed on different locations in three houses, marked with the red dots. Whenever the owner of each house opens or uses a piece of appliance, the corresponding sensor is activated. The start and the end time of each activation is then recorded. To label the human activity, the owner of each house wears a portable microphone and reports his or her activities throughout the day while doing them. Typical activities include sleeping, cooking, washing the hand, and using the bathroom. The sensor data and the activity log can therefore be easily matched up with each other, and we first discretized the data into 60-second chunks, transformed them into different forms, and then split them into training and test period to build our model and test the prediction accuracy. Naive Bayes model is the first and simpler model we tried. It assumes that each data point is independently and identically distributed. We modeled each sensor observation as an independent Bernoulli distribution and tried to maximize the joint posterior probability over the testing data points. The prior distribution here is the frequency an event occurs throughout the day, which could correct our model parameters from randomness. And naive Bayes model improved the prediction by taking observed sensor data into account. Next, we use hidden Markov chain model, which adds a chronological structure to the data. The key parameters for this model are the probability distribution of the next activity yt given the previous activity yt plus 1, namely the transition matrix, and also the probability distribution of observing certain sensor data xt given the current activity yt, namely the emission matrix. With pre-processed sensor data and activity logs, we train these parameters using Viterbi method, a maximum likelihood algorithm that iterates through all data samples and predicts the most likely true activity at each time step given the observed sensor data. Then, a second-order hidden Markov chain is implemented, aiming to improve prediction accuracy. With higher-order Markov chains, the current sensor observation is not only associated with the current underlying activity, but also past activities. Using a combination of multiple activities preserves more chronological information and significantly improves our model's predictive power, as shown in this heat map. We can observe that naive Bayes performs constantly well across all feature representations, whereas results from hidden Markov chain models depend on feature selection. Overall, the second-order Markov chain has the best prediction performance when the sensor data is represented by the signal changes.